Hi everyone. In this video we are going to discuss about the 18 electron rule. According to this rule, in an organometallic compounds and other complexes, the sum of valence shell electrons of transition metals or metal ion and electrons donated by the ligand is equal to 18. Then the requirement of this 18 electron rule come from the need to fulfill 1 s orbital, then 3 p orbitals and 5 d orbitals, and in each orbital we have to fill 2 electrons. So when we are adding whole together 2 plus 6 plus 10, there comes the need of 18 electrons. Then the close and stable valence shell configuration will be n minus 1 d10, ns2, np 6 electrons, and in transition metals the electrons of n minus 1d and ns electrons are considered to behave as valence electrons. Then we are moving on to a discussion how there are different behavior in transition metals. The first row transition metal carbonyls, mostly they will be obeying 18 electron rules, and each metal will be contributing the same number of electrons as the group number, and we all know carbonyl ligand will be donating 2 electrons, and pi backbonding makes no difference to the electron count of the metal. This is for the first row transition metals like scandium, titanium, vanadium, chromium, etc. So in the cases of transition metals with odd electrons, like if it is having odd electrons, even the number of electron 18 is never obeyed by adding 2 electron ligands like carbonyl ligand or any other ligand which is donating 2 electrons. In such cases, it will be very difficult. So, for example, consider the complex of vanadium hexacarbonyl like VCO6. That complex is having this kind of complex. It will be having 17 electrons, and this 17 electron complex is easily reduced to an 18 electron complex, that is, it will be reducing to this kind of anion. And in VCO6 the vanadium is too small to permit a 17th coordination site because there would be a strong steric hindrance. Therefore no metal bond, or that means this compound will not dimerize at all. Due to this reason, that the coordination of the 5th coordination species has more space available to make a metal-metal bond. In the case of MnCO5, it is having 17 electron species, and this MnCO5, it will be able to dimerize also. So each Mn will be having 18 electrons. That is because of the unpaired electron in each 5 coordinate species. Then likewise the cobalt complex CO4, it will be also able to dimerize, and in that case, in the case of cobalt, there will be a bridging CO ligand. Then when we are moving on to the further examples, chromium, then iron and nickel, all these metals will be bonding with 6, 5 and 4 ligands. Like chromium will be binding with 6 carbonyl ligands, iron will be binding with 5 carbonyl ligands, nickel will be binding with 4 carbonyl ligands to obtain this 18 electrons. The odd electron transition metals usually need to form metal-metal bonds. So that is the key point we have to focus. That means only the odd electron transition metals will be able to form a metal-metal bond like what we have seen in this vanadium complex. The complexes with coordination number 6 5 and 4 will be having, 6 will be having an octahedral structure, 5 will be having a trigonal or square pyramidal structure, and 4 will be having a tetrahedral or square planar structure. Not structure, geometries actually. So 18 electron rule complex, or the complexes which are obeying this 18 electron rule are considered to be stable. In most of the transition metal complexes, electrons are filled in the bonding molecular orbital and leaving the anti-bonding molecular orbital vacant. We all know when we are keeping an electron in the anti-bonding molecular orbital, we are considering that compound will be unstable. Since there are 9 bonding molecular orbitals, as I previously told, like 1 s orbital, 3 p orbital and 5 d orbital, and when we are adding these two electrons in them, whole together or maximum 18 electrons will be filled in them as predicted by the 18 electron rule, and because of that 18 electron rule, these complexes are considered to be stable. Thank you.